We're going to look at two exam style questions using the technique of Maclaurin's theorem to evaluate series expansions. And the first part of the question, it says write down the expansion of ln of 1 plus 2x. Now clearly, when it's written in this form, we can use the shortcut. We're being asked about ln of 1 plus 2x. So we can use the shortcut that we know for ln of 1 plus x, which is x minus x squared over 2 plus x cubed over 3 minus x to the 4 over 4. Not a factorial pattern in the denominator of this one. Okay, but don't forget you do get this in the formula booklet. So we want to go up to x cubed, so that would equal 2x minus 2x squared over 2 plus 2x cubed over 3, which would be 2x minus 2x squared plus 8x cubed over 3. It also says state the range of values for which the expansion is valid. Now, again from the formula booklet, the general expansion is valid between -1 and 1 for x. Clearly because you can't sub in -1 into the ln of 1 plus x because ln is undefined at 0, but obviously for our expansion, because our term is 2x, we would say 2x would have to be between those values. Oops, not included. So x would be greater than -1/2, less than or equal to 1/2. Again, we couldn't sub -1/2 into this, because that would mean we'd be evaluating ln of 0, which is undefined. Okay, now we get stuck into like the derivatives. Like, look what's happening now. We're going to get the first derivative, the second derivative, third derivative. And if you get a question like this in the exam, like straight away you want to be thinking, okay, Maclaurin Series expansions. Like, if we're finding derivatives, the Maclaurin Theorem allows us to sub-zero in, differentiate sub-zero in. So we're definitely being led down that route now, aren't we? Okay, remember for an ln function, the derivative is f dash over f, just using the shortcut from the chain rule. Okay, so we've got y equals ln of cos x dy by dx. The function's cos, so cos x on the bottom. Derivative on top, which is minus sine. So we could say that our first derivative is minus tan of x. Second derivative, we need to know that the derivative of tan is sec squared. Okay, you don't need to prove this using the quotient rule or anything like that. You just want to know that these trig derivatives, okay, because you've got enough going on without having to do them all from first principles. So that'll become minus sec squared. Think about that as minus sec squared, because we're going to have to differentiate it once more, so we can use the chain rule. We've got a function inside the function, so our third derivative. Again, remember the rule for a bracket to a power. If you've got a function to the power of n times by the power times by the derivative, take 1 off the power. So if we use that for this, times by the power times by the derivative of sec x, which is sec x tan x, again from the formula booklet, and take 1 off the power. So just tidying this up, we'd get minus 2 sec squared tan. It then says find the value of the fourth derivative when x is equal to 0. So we are going to have to differentiate once more, which might get a little bit messy. So if we were going to differentiate this, we could say u is equal to minus 2 sec squared and v is equal to tan. Times by the power. Times by the derivative, which is sec x tan x. Take 1 off the power. Derivative of tan is sec squared. And then we can apply the product rule. Just being attacked by a wasp. Hang on one sec. It's gone. Okay, so then we'd get minus 2 sec squared tan sec squared, which should be sec to the 4. Minus 4 tan squared sec squared. Now once we've got our fourth derivative, it says find the value of the fourth derivative when x is equal to 0. So if x is equal to 0, you don't want to be typing this into your calculator. Okay, you just need to realise that sec is 1 over cos, so that's like 1 over cos of 0. So all we need to know is what cos of 0 is. Cos of 0 is 1. Okay, so cos of 0 is 1, so this is 1 over 1. Also tan of 0 is 0, so minus. So as soon as one of the terms becomes 0, it all cancels. So we end up with minus 2. Okay. The question then says, hence, using Maclaurin's theorem, show that the first two non-zero terms in the expansion in ascending powers of x. So what we're trying to do is now we've got our derivatives for ln cos x. Now we're going to use the Maclaurin theorem to approximate this as this series here. Okay. There's only actually two terms, which means that we're going to be getting zeros when we sub in, but let's see what happens. Okay, I'll make a bit of space. Okay, so f of 0 would be equal to ln cos of 0, which is ln1, which is 0. F dash of 0 would be the first derivative was minus tan, so minus tan of 0, which is 0. Again, notice that like I'm showing, this answer is given to us, so we just need to be making sure we're getting these marks by showing where this comes from. The second derivative was equal to minus sec squared. So that would be minus 1 over cos of 0 squared. Cos of 0 is 1, so minus 1 over 1 squared, minus 1. Third derivative hopefully gives us 0, because there's no x cubed term in my expansion. But let's see. Third derivative was minus 2 sec, which is 1 over cos 0 squared times by tan of 0, and obviously tan of 0 is 0, so that's just clearly going to become 0. Okay, so the Maclaurin theorem tells us that f of x is equal to f of 0 plus f dash of 0x plus f double dash of 0 over 2 x squared. The pattern's factorial, so then it'd be over 6 x cubed. So we could say that f of x, in other words, ln of cos x, f of 0, which is 0, f dash of 0, which is also 0. Second derivative was minus 1, so that'd be minus 1 over 2x squared. The fourth derivative was minus 2, and then the fourth derivative is divided by 4 factorial, okay, which is 24. And I would show that because like it's just like a little bit more to justify the answer that we're getting, instead of just writing the answer down, you know. Minus a half x squared, minus 1 over 12x to the 4. Okay, now that we've got our series expansions, we're asked to evaluate a limit. So clearly we're going to be using the answers that we've got in the question. And if we can write it as a polynomial, hopefully we'll be able to evaluate the limit as x tends to 0. Okay, so we think about the limit as x tends to 0 of x times by ln of 1 plus 2x, which we can write as 2x minus 2x squared plus 8 over 3x cubed. I always like to write like plus dot 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 just to illustrate that I know that this is like an infinite expansion. And once we've cancelled, we can see that like all those other terms, as x tends to 0, all those other terms would also disappear as well. But it's just good practice to show that you know there's more terms in this expansion. Then we've got x squared minus, use a bracket, ln cos x, we can write as minus a half, x squared minus 12, x to the 4 plus dot 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 again, because there's more terms here, but they're all going to cancel. And then we've got the limit as x tends to 0 of two x squared minus 2x cubed plus 8 over 3 x to the 4. X squared minus minus, so plus a half, x squared would be 3 over 2 x squared plus 1, 12 x to the 4. And remember the key step now is to cancel down common factor of x squared in everything, so it would be 2 minus 2x plus 8 over 3 x squared and 3 over 2 plus 12x squared. And clearly now we can see, well, because we're thinking about as x tends to 0, all these other terms would be tending to 0, wouldn't they? Like minus 2x would tend to 0, 8 over 3x squared, so everything would disappear and we'd be left with our limits that we're trying to evaluate. Therefore the limit as x tends to 0 of this would be equal to 2 divided by 3 over 2, also known as 4 over 3. Okay. Okay, we'll try one more example. Slightly different style of question, this one, because we've got this like y dy by dx notation, and like if this comes up, right, what I would recommend is, I don't know if you're going to be able to see this if I write it. When you see something like this, think about implicit. Can you see that? Think about an implicit derivative. All will become clear in a second, like when we do the question, okay? But that's like a little bit of a clue. If they're writing the derivatives in terms of like y and x, it's probably a lot easier if you approach this question using implicit differentiation. You'll see why when we start, okay? So we've got y is equal to 4 plus sine x, all to the power of 0.5, so the square root of 4 plus sine x. And it says express y dy by dx in terms of cos x. So clearly, like we're just being hit with some sort of derivative, but like later on, it's going to lead us into a Maclaurin series expansion. We're aiming to go up to the third derivative as well. But let's start by figuring, well, how could I figure out what y dy by dx is? So, well, if I know what y is, let's just differentiate and see what happens. So apply the chain rule, times by the power, times by the derivative. Take one off the power. Okay. I don't like that. I'm going to write it as a half. Okay. So times by the power, times by the derivative, take one off the power. Therefore, y dy by dx would equal 4 plus sin x. It's the 0.5 times by 1/2 cos x. 4 plus sin x minus 0.5. And notice that what happens here is because the powers 0.5 and minus 0.5, they cancel each other out. And we're left with y dy by dx would equal to 1/2 cos x. Okay, there's a reason that they're doing this, they're trying to help you. Because now, look, if you don't spot this, you're going to get into a bit of a mess, and also you're going to waste a lot of time as well. Like now it wants us to find the first derivative. But look at the first derivative. If you focus purely on that first derivative, and then you're going to have to use the product rule, you've also got a chain rule. The second derivative is going to be difficult enough. The third derivative will be a complete mess. And like, it is doable, but like it's not the most efficient way of doing it. We know that y dy by dx is equal to 1/2 cos x. So use this, because you can find the second derivative and you can find the third derivative from this equation. Okay, obviously we just got to use the product rule on the left hand side. So if I differentiate the whole equation with respect to x on both sides, the derivatives are so much easier. Okay, I'm going to have to use the product rule on this side. So u times by dv, so if I differentiate this, that would be d2 y by dx squared. Because remember, we're differentiating with respect to x, so if we differentiate y by dx, it's d2 y by dx squared. Plus, now this is where you've got to be careful, you've got to differentiate y with respect to x, so that would be dy by dx times by dy by dx. And you might have never seen that before. It's not the same as d2y by dx squared. It's dy by dx all squared. I might have gone a little bit quick there, like essentially if you wanted to write u equals y, v equals dy by dx, du by dx would equal dy by dx, and dv by dx. Remember, we're differentiating with respect to x would be d2y by dx squared. And so by using the product rule, this is what we end up with. Okay? And then on the right hand side, cos differentiates to minus sine, so it'll be minus 1/2 sine x. So I've got y d2y by dx squared plus dy by dx squared equals minus 1/2 sine x. We need to get to the third derivative. Okay, so if we differentiate again with respect to x, product rule, so that would be y d3 y by dx cubed plus dy by dx times by d2y by dx squared plus chain rule, function inside the function, times by the power, times by the derivative, which would be d2y by dx squared. Take one off the power, and that would equal the derivative of this. Minus sign goes to minus cos, so minus 1/2 cos x. Now you might think that wasn't easy, and yeah, okay, the first time you see this, it's not actually immediately obvious, and it's not, you've got to be confident with your implicit differentiation, but it is going to be slightly quicker, I think, if we do it this way. I mean, you try for yourself, you can try it the other way, you can just differentiate this 3 times and see what happens. Like, it is doable, but I just thought it's nice to see this implicit technique. Have we actually answered the question? The question says find the value of d3y by dx cubed when x equals 0. So once we've got all these derivatives, we can then start to like sub-zero in. So we know that when x equals 0, y would equal sine of 0 is 0, fourth power 0.5, so we know y equals 2. Okay? Then we can go and figure out what dy by dx is. Okay, because we know when x equals 0, y equals 2. Now we can find out what dy by dx is. So we've got y dy by dx equals a half cos x. So 2 dy by dx would equal a half cos of 0. Dy by dx would equal, cos of 0 is 1. So dy by dx would equal a quarter. So now we know x equals 0, y equals 2. We know dy by dx equals a quarter. We've got this equation which tells me about my second derivative. Okay, so if we sub into this one, we can find the second derivative. So y, which is 2 d2 y by dx squared plus dy by dx all squared, which is a quarter, all squared, equals minus a half sine of 0. Now sine of 0 is 0. Okay, so we've got d2y by dx squared. A quarter squared would be 1/16, so that would be minus 1/16. So then we can divide by 2 to get d2y by dx squared equals minus 1/32. Finally, we just need to figure out the third derivative. Okay, so we've got y, which is 2 d3y by dx cubed, which is what we're trying to find, plus dy by dx, which is a quarter. Second derivative, which is minus 1/32. 2 lots of second derivative times my first derivative. And that would equal minus a half times by cos of 0, which is 1. Okay, stay with me, we're nearly there, so we can figure out what d3 y by dx cubed is. Okay, so I'm getting, by rearranging, I've got this, so we get d3 y by dx cubed will be minus 61 divided by 256. Okay, now that is quite long-winded, but the beauty of this technique, right, now that we've got all of our derivatives evaluated when x equals 0, the next part of the question, or the last part of the question, says hence by using the Maclaurin Theorem, find the first 4 terms in this expansion. And we've done all the work for this. Like we've got our f of 0, we've got our f dash of 0, we've got our f double dash of 0, we've got our f triple dash of 0. So we can now write relatively quickly the series expansion, because by doing it implicitly, we've had to figure out what all of the values for all of the derivatives are up to that point, haven't we? So we've got f of 0 plus f dash 0x plus f double dash 0x squared over 2 plus f triple dash 0 x cubed over 6. So we can say that 4 plus sine x to the 0.5 would be equal to first 4 terms. Okay, so the first term would be f of 0, which is our y value, which is 2. F dash, which is our first derivative, would be a quarter x. F double dash, which was minus 1/32 divided by 2 x squared. And the third derivative, which was minus 61/256. 6. That's divided by 6. X cubed. So we get 2 plus a quarter x minus 1 over 64. X squared minus 61 over 1536. X cubed. Alright. Nice one, guys.